November 12, 1943, 0847 hours. 27,000 feet above the industrial heartland of Nazi Germany, American B-24 Liberator formations drone eastward through crystalline morning air, their Pratt and Whitney engines carving contrails across a hostile sky. In the belly of each bomber, suspended in a 4-foot diameter sphere of aluminum and plexiglass, ball turret gunners peer through optical glass between their elevated feet, scanning the blue void below for the glint of approaching Messerschmitt fighters. The hydraulic systems hum with electric precision while K4 computing sites calculate ballistic solutions that will determine who lives and who dies in the next 60 seconds. Obergefreiter Wilhelm Hartmann of Jagdgeschwader 26 rolls his Focke-Wulf 190 into a climbing turn, the supercharger whining as he gains altitude for what should be a textbook attack on the American bomber formation. At 24 years old, Hartmann has 17 confirmed kills painted on his fighter's fuselage, but he has never encountered the new defensive systems that Sperry Corporation engineers have been installing in these 4-engine monsters since early 1942. The intelligence briefings at his squadron's morning Lagebesprechung mentioned increased defensive firepower, but nothing prepared him for what happens next. Staff Sergeant Anthony Torino, a 19-year-old former steel worker from Pittsburgh, adjusts his position inside the cramped ball turret of B-24H made in America, his knees drawn up against his chest in the fetal position that every ball turret gunner learns to endure for missions lasting 8 to 10 hours. The Sperry K4 gunsight hangs 18 inches from his face, its electromechanical computing elements already fed with the wingspan data for Focke-Wulf 190 fighters, 34.5 feet from wingtip to wingtip. Through the circular optical window between his boots, Torino spots the approaching German fighter formation, 12 black specks climbing rapidly from the southeast. The ball turret system represents the culmination of American industrial engineering applied to aerial warfare, a marriage of Sperry Corporation's gyroscopic expertise with Briggs Manufacturing Company's automotive precision. Each turret contains 2 Browning and M250 caliber machine guns capable of firing 750 to 850 rounds per minute, fed by stainless steel ammunition containers holding 250 rounds per gun. The K4 computing gun sight, manufactured under license from Sperry Gyroscope Company, functions as an analog computer decades before digital systems exist, automatically calculating lead angles and bullet drop compensation based on target range and angular velocity. Hartmann's attack formation approaches from below and behind, exactly as Luftwaffe tactical doctrine prescribes for engaging American heavy bombers. The German pilot has studied captured B-17 Flying Fortress defensive armament charts that show minimal coverage beneath the aircraft's belly, but these intelligence reports are 18 months old and fail to account for the revolution in defensive firepower that American engineers have achieved. As his Focke-Wulf 190 closes to 800 meters range, Hartmann sees something that makes his blood freeze in his veins. The unmistakable silhouette of a spherical gun turret rotating beneath the bomber's fuselage, twin machine gun barrels tracking his approach with mechanical precision. Inside the ball turret, Torino's left foot depresses the range pedal of his K4 gunsight while his eyes focus on the approaching fighter through the optical reticle system. The computing sight's vertical lines frame the Focke-Wulf's wingspan perfectly as the German fighter reaches 1,000 yards range, exactly as Sperry's engineers designed the system to function. The electromechanical computer calculates bullet trajectory, accounting for the bomber's forward velocity, the fighter's closing speed, and the gravitational drop of 50 caliber projectiles over the next 4 seconds of flight time. Torino's right hand grips the firing trigger while hydraulic motors rotate the turret assembly, keeping the German fighter centered in his sights. At Sperry Corporation's factory complex in Lake Success, Long Island, production manager James McKenzie reviews the morning shift reports from the ball turret assembly line where women workers in coveralls install precision machined components into each defensive system. The company has received contracts for over 15,000 ball turrets since 1941, with subcontracting arrangements that include Steel Products Engineering Company for upper turret components and Vickers Incorporated for hydraulic power units. Each turret requires 47 separate machined parts, 18 feet of electrical wiring, and 6 hydraulic fluid lines, all assembled to tolerances measured in thousandths of an inch. Hartmann fires his first burst at 600 meters range, the Focke-Wulf's 4 Mauser MG 151 20mm cannons and twin MG-17 machine guns lighting up the morning sky with tracer rounds. But the American bomber's evasive maneuvering, combined with the extreme difficulty of hitting a target from a high-speed diving attack, causes most of his shells to miss their mark completely. German gunnery instructors at Luftwaffe training schools teach that average pilots achieve only 2% accuracy against heavy bomber targets, meaning that destroying a single B-24 Liberator requires approximately 1,000 rounds of 20mm ammunition. Hartmann's Focke-Wulf carries only 500 rounds total. The ball turret's response is immediate and devastating. Torino squeezes his firing trigger as the German fighter enters the computed engagement zone, and twin streams of 50 caliber bullets converge on Hartmann's Focke-Wulf with mathematical precision. The K4 gun sight has calculated the exact point in space where aircraft and bullets will meet, and the hydraulic tracking system maintains perfect aim despite the bomber's forward motion and the fighter's evasive maneuvers. Each 50 caliber projectile weighs 45 grams and travels at 2,800 feet per second, carrying enough kinetic energy to penetrate armor plating and destroy aircraft engines. Hartmann's fighter staggers as multiple 50 caliber rounds punch through his starboard wing root, severing hydraulic lines and destroying the aileron control cables. The Focke-Wulf's BMW 801 radial engine begins streaming white coolant vapor as more bullets find their mark, and Hartmann realizes with growing horror that the American defensive system is far more accurate than anything described in Luftwaffe intelligence briefings. He pulls out of his attack run and dives away from the bomber formation, his damaged fighter trailing smoke and losing altitude rapidly. Similar encounters repeat themselves across the bomber stream as German pilots discover the lethal effectiveness of American ball turret gunnery. Hauptmann Ernst Schroeder of Jagdgeschwader II leads his Staffel in a coordinated attack on a B-24 formation, but loses 3 fighters in less than 2 minutes to the devastating accuracy of Sperry ball turrets. The mathematical precision of the K4 computing sites transforms American gunners from desperate defenders into calculated executioners, each engagement resolved by ballistic algorithms rather than luck or pilot skill. The statistical data compiled by American intelligence officers tells the story in stark numerical terms. Between November 1943 and April 1944, B-24 Liberator ball turrets engage 53 enemy fighters over Nazi-occupied Europe, destroying 30 aircraft for a kill ratio of 57%. This effectiveness rating exceeds every other defensive gun position on American heavy bombers, including the tail turrets that German pilots have learned to fear during head-on attacks. The psychological impact on Luftwaffe fighter pilots proves equally significant, as captured German airmen reveal during prisoner-of-war interrogations that they prefer attacking bomber formations from above rather than below, specifically to avoid ball turret engagement zones. Technical Sergeant Robert Chun, a 22-year-old mechanical engineering student from San Francisco, experiences his first combat mission as ball turret gunner aboard B-24J Pacific Punisher during a raid on the Messerschmitt 109 production facility at Regensburg. The cramped confines of the Sperry ball turret force Chun to assume the standard fetal position, with his back pressed against the rear armor plating and his knees drawn up to accommodate the turret's 3.5-foot diameter. The electric heating elements in his flight suit combat the -30-degree temperature at bombing altitude, while the K4 computing site provides the only illumination in the darkened turret interior. Chen's baptism by fire comes at 0923 hours, when a formation of Messerschmitt 109G fighters from Jagdgeschwader 53 attacks the bomber stream from the south. The German pilots employ the standard Luftwaffe fighter tactics developed during 3 years of combat against American heavy bombers, approaching in line abreast formation at high speed to minimize their exposure time to defensive gunfire. But they have not encountered the technological revolution that Sperry Corporation engineers have achieved with their ball turret defense systems. Lieutenant Friedrich Weber, a veteran pilot with 21 confirmed victories, leads the German attack formation in his Messerschmitt 109G6. The fighter carries a single 30mm 108 Malawian Quachas cannon and 2 13mm MG 131 machine guns, weapons specifically chosen for their effectiveness against American heavy bomber construction. Weber has studied captured B-17 Flying Fortress technical manuals that detail the aircraft's defensive blind spots, but these documents predate the widespread installation of Sperry ball turrets on American bombers. As Weber's fighter closes to 400 meters range, Chun tracks the approaching Messerschmitt through his K4 optical sight system. The computing mechanism automatically calculates the ballistic solution as Chun adjusts the range setting to match the fighter's wingspan within the vertical reticle lines. The electromechanical computer processes the target's angular velocity, closing speed, and altitude differential, generating firing commands that position the twin 50 caliber machine guns with mechanical precision. Chen's feet rest on the hydraulic control pedals while his hands grip the firing triggers, every movement transmitted through the turret's electrical systems. Weber opens fire with his 30mm cannon at 300 meters range, the massive shells designed to destroy American bomber engines with single hits. But the extreme difficulty of accurate gunnery from a high-speed fighter platform, combined with the B-24's defensive maneuvering, causes most of his shots to miss their intended targets. The few shells that do connect with the bomber's fuselage create spectacular explosions but fail to bring down the four-engine giant, which continues flying toward its target despite visible battle damage. Chen's response demonstrates the technological superiority of American defensive systems. The ball turret's K4 computing site has maintained perfect tracking throughout Weber's attack run, and Chen fires a sustained burst of 50 caliber bullets that converge on the Messerschmitt 109 with mathematical accuracy. The German fighter absorbs multiple hits to its Daimler-Benz engine and cockpit section, and Weber feels his aircraft shudder as critical systems fail under the impact of armor-piercing projectiles. Smoke pours from the engine cowling as the Messerschmitt enters an uncontrolled dive toward the earth below. The combat effectiveness data compiled by 8th Air Force intelligence analysts reveals the devastating impact of American ball turret systems on German fighter operations. Luftwaffe fighter losses increase dramatically whenever bomber formations employ coordinated defensive gunnery, with ball turret gunners accounting for a disproportionate number of enemy aircraft destroyed. The psychological pressure on German pilots intensifies as word spreads through fighter squadrons that attacking American bombers from below has become tantamount to suicide. Sperry Corporation's manufacturing facilities operate around the clock to meet the demands of American bomber production, with factory workers installing ball turrets in Boeing B-17 Flying Fortress and consolidated B-24 Liberator aircraft as quickly as they roll off the assembly lines. The company's engineering department continues refining the K4 computing site system, incorporating lessons learned from combat reports that arrive daily from the European theater of operations. Each technical improvement increases the system's accuracy and reliability, transforming American bombers into flying battleships capable of defending themselves against the most determined fighter attacks. The strategic implications become clear to German high command as Luftwaffe fighter losses mount throughout the winter of 1943 and spring of 1944. General der Jagdgeschwader Adolf Galland issues tactical directives instructing fighter pilots to avoid attacking American bomber formations from below, acknowledging that ball turret defensive systems have made traditional attack profiles obsolete. The psychological impact on German fighter pilots proves equally significant, as the realization spreads that American industrial technology has shifted the balance of air combat decisively in favor of the bombers. Staff Sergeant Maria Santos, one of the first female ball turret gunners to serve aboard a B-24 in the Pacific Theater, experiences combat against Japanese fighter aircraft during the March 1944 raids on Truk Lagoon. The confined space of the Sperry ball turret poses additional challenges for Santos, whose smaller stature actually proves advantageous in the cramped fighting compartment that was originally designed for the shortest male crew members. The K4 computing site functions identically regardless of the gunner's gender, its electromechanical systems calculating ballistic solutions based purely on mathematical principles. Santos encounters her first enemy aircraft at 1,147 hours when a formation of Mitsubishi A6M0 fighters from the Imperial Japanese Navy's 201st Air Group attempts to intercept the American bomber formation. The Japanese pilots employ different tactics than their German counterparts, relying on superior maneuverability rather than firepower to defeat American defensive systems. But the mathematical precision of the ball turret's K4 computing site proves equally effective against Japanese fighter aircraft, regardless of their tactical approach or pilot skill. Flight Petty Officer Hiroshi Tanaka, a veteran Zero pilot with 15 confirmed victories, leads the Japanese attack formation in a coordinated assault on the B-24 bomber stream. Tanaka has studied captured American aircraft and believes that the Zero's superior agility will allow him to evade the relatively slow-tracking defensive turrets while delivering accurate cannon fire against the bomber's engines and fuel tanks. This tactical assessment proves fatally flawed when confronted with the technological sophistication of American ball turret systems. Santos tracks Tanaka's Zero through her optical sight system as the Japanese fighter approaches from the southwest, its distinctive silhouette clearly visible against the blue Pacific sky. The K4 computing site automatically calculates the ballistic solution as Santos inputs the Zero's wingspan data, 39.4 feet, into the mechanical computer system. The electromechanical components process the target's flight path and generate firing commands that position the twin 50 caliber machine guns with mechanical precision. Tanaka opens his attack run at 600 meters range. The Zero's two 20mm Type 99 cannons and twin 7.7mm machine guns blazing as he dives toward the American bomber formation. The Japanese fighter's lightweight construction allows for exceptional maneuverability, but this same characteristic makes it extremely vulnerable to 50 caliber machine gun fire. American armor-piercing bullets can penetrate the Zero's thin aluminum skin and destroy critical systems with relative ease. Santos fires a sustained burst as Tanaka's Zero enters the computed engagement zone, and the mathematical precision of the ball turret system immediately becomes apparent. Twin streams of 50 caliber bullets converge on the Japanese fighter with ballistic accuracy that eliminates the element of chance from aerial combat. Tanaka's Zero absorbs multiple hits to its engine and cockpit sections, the lightweight aircraft structure offering minimal protection against armor-piercing projectiles traveling at 2,800 feet per second. The Zero begins trailing black smoke as its Nakajima Sakai radial engine suffers catastrophic damage from repeated 50 caliber hits. Tanaka attempts to break off his attack and escape to lower altitude, but the ball turret's hydraulic tracking system maintains perfect aim throughout his evasive maneuvers. Additional bullets penetrate the fighter's fuel tanks, and the Zero explodes in a ball of orange flame as aviation gasoline ignites. Tanaka's aircraft disintegrates completely, leaving only a cloud of burning debris falling toward the Pacific Ocean below. Imperial Japanese Navy intelligence officers compiled detailed reports on American bomber defensive systems following these engagements, recognizing that ball turret technology represents a fundamental shift in the balance of aerial warfare. The mathematical precision of American gunnery systems eliminates many of the tactical advantages that Japanese pilots have relied upon throughout the Pacific War, particularly the superior maneuverability of Zero fighters. Combat effectiveness data shows that Japanese fighter losses increase dramatically when engaging American bomber formations equipped with ball turret defense systems. The technological sophistication of American ball turret systems becomes even more apparent during encounters with Italian Regia Aeronautica fighter aircraft over the Mediterranean theater. Italian pilots flying Macchi MC-202 and MC-205 fighters discover that their aircraft's limited armament and relatively low top speed make them particularly vulnerable to the accurate defensive fire generated by Sperry ball turrets. The Macchi fighters carry only two 12.7mm machine guns and a single 20mm cannon, insufficient firepower to destroy American four-engine bombers quickly enough to avoid return fire. Tenente Colonnello Giuseppe Marcelli, commanding officer of the 51st Stormo Caccia, leads his squadron of MC-205 fighters in an attack on B-24 Liberators during a raid on the Plosti oil refineries in Romania. Marcelli has 23 confirmed victories to his credit, but he has never encountered the defensive systems that American engineers have installed in their latest bomber models. The Italian pilot's tactical knowledge is based on intelligence reports compiled during 1942, before Sperry Corporation ball turrets became standard equipment on American heavy bombers. Marcelli's attack formation approaches the bomber stream from high altitude, diving toward the B-24s in a coordinated assault designed to overwhelm the American defensive gunners through speed and concentration. The Italian pilots employ proven tactics developed during combat against British bomber formations, but these techniques prove inadequate against the technological sophistication of American ball turret systems. The mathematical precision of K4 computing sites eliminates many of the tactical advantages that Italian pilots have relied upon during earlier campaigns. Technical Sergeant Joseph Romano, a 20-year-old ball turret gunner from Chicago, tracks the approaching Italian fighters through his optical sight system aboard B-24H. Windy City warrior Romano's family emigrated from Sicily in 1919, and the irony of fighting against aircraft bearing Italian markings is not lost on the young gunner as he prepares to engage the MC-205 formation. The K-4 computing site functions without regard for nationality or politics, its electromechanical systems calculating ballistic solutions based purely on mathematical principles. Romano inputs the MC-205 wingspan data, 34.8 feet, into his computing site as Marcelli's fighter closes to engagement range. The Italian aircraft approaches at high speed in a shallow diving attack, its single 20mm cannon and twin 12.7mm machine guns firing long bursts at the American bomber formation. But the MC-205's relatively light armament requires multiple hits to destroy a 4-engine bomber, providing ample opportunity for the ball turret's defensive systems to respond with lethal accuracy. The mathematical precision of Romano's K-4 computing site becomes immediately apparent as twin streams of 50 caliber bullets converge on Marcelli's MC-205 with ballistic accuracy. The Italian fighter absorbs multiple hits to its Daimler-Benz engine and wing structures, critical systems failing under the impact of armor-piercing projectiles. Marcelli feels his aircraft shudder as hydraulic lines sever and control cables part, the MC-205 becoming increasingly difficult to control as battle damage accumulates. Black smoke pours from the Italian fighter's engine cowling as coolant systems fail under repeated 50 caliber impacts. Marcelli attempts to break off his attack and dive away from the bomber formation, but the ball turret's hydraulic tracking system maintains perfect aim throughout his evasive maneuvers. Additional bullets penetrate the MC-205's fuel tanks and cockpit section, and Marcelli realizes that his aircraft has sustained fatal damage. He rolls the fighter inverted and pulls the canopy release, bailing out at 18,000 feet altitude, while his MC-205 spirals toward the earth below. The combat effectiveness statistics compiled by Mediterranean Allied Air Force's intelligence sections reveal the devastating impact of American ball turret systems on Axis fighter operations throughout the theater. Italian fighter losses increased dramatically during engagements with American bomber formations, particularly when attacking from below where ball turret defensive zones provide maximum coverage. Regia Aeronautica tactical doctrine evolves to emphasize high-altitude attacks and hit-and-run techniques, acknowledging that traditional fighter versus bomber tactics have become obsolete in the face of American technological superiority. The manufacturing process at Sperry Corporation's Long Island facilities represents one of the most sophisticated production operations in American industry during World War II. Each ball turret requires precision machining of aluminum castings, assembly of electromechanical computing components, and installation of hydraulic systems that must function reliably under extreme combat conditions. Quality control inspectors test every component to tolerances measured in thousandths of an inch, ensuring that K-4 computing sites will calculate ballistic solutions accurately regardless of altitude, temperature, or aircraft maneuvering. Female workers comprise a significant portion of Sperry Corporation's assembly line workforce, their smaller hands and attention to detail proving ideal for installing the intricate wiring harnesses and optical components that make ball turret systems function. Rose McKinnon, a former telephone operator from Brooklyn, assembles K-4 computing site mechanisms on the day shift, carefully installing gyroscopic elements and mechanical calculators that will determine the outcome of aerial combat over Nazi Germany. Each site requires 47 separate adjustments and calibrations before it meets military specifications. The strategic impact of American ball turret technology extends far beyond individual combat engagements, fundamentally altering the tactical balance of aerial warfare over Europe and the Pacific. Luftwaffe and Imperial Japanese Navy intelligence officers compile extensive reports on American defensive systems, recognizing that Sperry ball turrets have eliminated many of the tactical advantages that Axis fighter aircraft previously enjoyed. The mathematical precision of American gunnery systems forces enemy pilots to develop new attack techniques, often at the cost of reduced effectiveness and higher casualty rates. German fighter pilot training programs modify their curricula to address the threat posed by American ball turret systems, emphasizing high-speed slashing attacks and coordination with anti-aircraft artillery rather than traditional fighter versus bomber tactics. Luftwaffe technical officers study captured American equipment and attempt to develop countermeasures. But the sophistication of Sperry Corporation's electromechanical computing systems proves difficult to duplicate with German industrial resources increasingly strained by Allied bombing campaigns. The psychological impact on Axis fighter pilots proves equally significant as word spreads through combat squadrons that attacking American bombers from below has become extremely hazardous. Veterans describe the mathematical precision of ball turret gunnery in terms that emphasize the mechanical, inhuman nature of American defensive systems. Unlike traditional aerial combat that relies on pilot skill and aircraft performance, engagement with ball turret gunners resembles fighting against a calculating machine that never misses its calculations. Staff Sergeant Thomas Kowalczyk, a Polish-American ball turret gunner from Detroit, experiences his most intense combat during the February 1944 raids on aircraft manufacturing facilities in central Germany. The cramped confines of his Sperry ball turret become both sanctuary and prison as German fighters mount determined attacks on his B-24 formation, their pilots driven by desperation as Allied bombing campaigns intensify pressure on Nazi industrial production. Kowalczyk's K-4 computing site tracks multiple targets simultaneously, while hydraulic motors rotate the turret assembly to engage each threat in succession. The February raids represent the climax of American strategic bombing efforts against German aircraft production, with over 800 B-17 and B-24 bombers attacking targets throughout the Reich during a week-long campaign that historians will later call Big Week. Ball turret gunners like Kowalczyk find themselves at the center of the most intense aerial battles of the European War, their mathematical precision determining whether bomber formations reach their targets or fall victim to Luftwaffe interceptors. German fighter pilots respond with unprecedented ferocity, mounting coordinated attacks involving over 300 Messerschmitt 109 and Focke-Wulf 190 fighters during single missions. The intensity of combat reaches levels that strain both aircraft and aircrew to their breaking points, with ball turret gunners engaging multiple targets during battles that last for hours. Kowalczyk's B-24 absorbs battle damage from cannon shells and machine gun bullets, but the Sperry ball turret continues functioning despite hits that disable other aircraft systems. The technological reliability of American ball turret systems proves crucial during these intense engagements, with K-4 computing sites maintaining accuracy despite battle damage and extreme environmental conditions. Emergency power systems allow ball turrets to continue operating even when main electrical systems fail, and manual backup controls enable gunners to engage targets when hydraulic systems are damaged. This redundancy reflects the sophisticated engineering that Sperry Corporation incorporates into every defensive system. Combat effectiveness data compiled during Big Week reveals the decisive impact of American ball turret technology on the aerial battles over Germany. Despite facing the most determined Luftwaffe resistance of the entire war, American bomber formations achieved their objectives while inflicting disproportionate losses on German fighter squadrons. Ball turret gunners account for a significant percentage of enemy aircraft destroyed, their mathematical precision proving more effective than traditional gunnery techniques that rely on pilot instinct and experience. The strategic consequences of American ball turret effectiveness become apparent in German aircraft production statistics compiled after the war. Luftwaffe fighter strength declines rapidly during 1944, as pilot losses mount and aircraft manufacturing facilities suffer repeated bombing attacks. The mathematical precision of American defensive gunnery eliminates experienced German pilots who cannot be easily replaced, creating a spiral of declining effectiveness that ultimately contributes to Nazi Germany's defeat. Imperial Japanese Navy aviation faces similar challenges in the Pacific theater as American ball turret technology proves equally effective against Japanese fighter aircraft. The lightweight construction of Zero fighters makes them particularly vulnerable to .50 caliber machine gun fire, while their limited armament requires extended exposure to defensive gunfire to achieve bomber kills. Japanese pilots develop new tactics emphasizing high-speed attacks and coordination with land-based anti-aircraft artillery, but these modifications cannot entirely overcome the technological advantages of American defensive systems. The human cost of ball turret operations becomes apparent in casualty statistics compiled by American medical officers during the European and Pacific campaigns. Despite the statistical effectiveness of ball turret gunnery, gunners themselves face significant risks from enemy fire, aircraft accidents, and the extreme environmental conditions encountered during high-altitude combat. The confined space of the turret, combined with the inability to wear parachutes during combat operations, creates psychological pressures that test the limits of human endurance. Medical examinations of ball turret gunners reveal the physical toll exacted by prolonged operations in cramped quarters, with many developing chronic back problems and circulation disorders from maintaining fetal positions during 8 to 10-hour missions. The psychological impact proves equally significant, with some gunners suffering from claustrophobia and anxiety disorders related to their isolation from the rest of the bomber crew. Despite these challenges, ball turret gunners maintain some of the highest morale ratings in the Army Air Forces, taking pride in their technological superiority and combat effectiveness. The post-war analysis of American ball turret technology reveals its significance in the broader context of World War II's technological revolution. Sperry Corporation's integration of gyroscopic stabilization, electromechanical computation, and precision manufacturing represents a quantum leap in defensive weapon systems, establishing principles that influence military technology development for decades. The mathematical precision achieved by K4 computing sites prefigures the computer-controlled weapon systems that dominate modern warfare. German and Japanese engineers attempt to reverse-engineer captured American ball turret components, but the sophistication of Sperry Corporation's manufacturing processes proves difficult to duplicate under wartime conditions. The precision machining required for K4 computing sites exceeds the capabilities of most Axis industrial facilities, while the integration of multiple technologies into a single system requires engineering expertise that few organizations possess. American industrial superiority becomes apparent not just in quantity but in the technological sophistication of weapons systems. The legacy of American ball turret technology extends far beyond World War II, influencing the development of guided missiles, computer-controlled artillery, and automated defense systems. The principles of ballistic computation pioneered by Sperry Corporation engineers find application in space program navigation systems and modern air defense networks. The mathematical precision that made ball turret gunners so effective against Axis fighter aircraft establishes the foundation for technological developments that continue shaping warfare in the 21st century. Staff Sergeant Michael O'Brien, a ball turret gunner aboard B-24 Irish Rose, participates in the final major air battle over Germany during April 1945. The war's outcome is no longer in doubt, but Luftwaffe pilots continue mounting desperate attacks against Allied bomber formations, their motivations shifting from military objectives to pure survival instinct. O'Brien's Sperry ball turret engages the last generation of German fighter aircraft, including jet-powered Messerschmitt 262s whose revolutionary technology cannot overcome the mathematical precision of American defensive systems. The April 1945 engagements demonstrate the continued effectiveness of ball turret technology even against the most advanced Axis aircraft. German Me-262 jets possess speed advantages that should theoretically allow them to evade conventional defensive fire, but the predictive capabilities of K4 computing sites enable ball turret gunners to engage targets moving at speeds exceeding 500 miles per hour. The mathematical principles underlying American gunnery systems prove adaptable to new tactical situations, maintaining their effectiveness despite technological advances in enemy aircraft. O'Brien's final combat mission occurs during the April 25 raid on the Škoda armament works in Czechoslovakia, one of the last strategic bombing operations conducted by American heavy bombers in Europe. German resistance has become sporadic and disorganized, but individual fighter pilots continue intercepting bomber formations with determination born of desperation. O'Brien engages a lone Messerschmitt 109 whose pilot makes a suicidal attack against the American formation, both aircraft and aircrew bearing the psychological scars of 4 years of increasingly hopeless warfare. The German pilot, Obergefreiter Hans Weber, flies his final mission in a Messerschmitt 109K4 bearing the scars of multiple combat encounters. Weber has survived longer than most Luftwaffe fighter pilots, his skill and luck carrying him through battles that consumed entire squadrons of less experienced aviators. But on this April morning, mathematical precision trumps pilot skill as O'Brien's ball turret tracks the approaching fighter with mechanical accuracy that eliminates human error from the engagement equation. Weber's Messerschmitt absorbs multiple 50 caliber hits as it closes with the American bomber formation, the fighter's Daimler-Benz engine streaming coolant vapor while control surfaces fragment under the impact of armor-piercing projectiles. The German pilot maintains his attack despite catastrophic aircraft damage, his determination reflecting the psychological state of Luftwaffe personnel during the war's final weeks. Weber's fighter crashes into a Bohemian forest, the pilot's body never recovered from the wreckage of his once proud Messerschmitt 109. The statistical summary of American ball turret operations during World War II reveals the system's decisive impact on the aerial campaigns over Europe and the Pacific. Over 30,000 Sperry ball turrets see combat service aboard B-17 Flying Fortress and B-24 Liberator bombers, accounting for a significant percentage of Axis fighter aircraft destroyed by defensive gunfire. The mathematical precision of K-4 computing sites transforms American bombers from vulnerable targets into effective defensive platforms, fundamentally altering the tactical balance of aerial warfare. The human cost of this technological revolution becomes apparent in the casualty statistics compiled by both sides during the conflict. American ball turret gunners suffer significant losses during the intensive aerial campaigns of 1943 and 1944, but their effectiveness in destroying enemy fighters saves countless bomber crews from certain death. Axis fighter pilot casualties mount steadily as the war progresses, the mathematical precision of American defensive systems eliminating experienced aviators who cannot be easily replaced under wartime conditions. The broader implications of American ball turret technology extend beyond immediate military applications, demonstrating the decisive advantages that flow from superior industrial organization and technological innovation. Sperry Corporation's ability to mass-produce sophisticated defensive systems reflects the depth of American engineering capability and manufacturing infrastructure, advantages that prove crucial in determining the war's outcome. The integration of multiple technologies into effective weapons systems establishes principles that continue influencing military development decades after the conflict's conclusion. The final tally of ball turret effectiveness validates the investment that American industry made in advanced defensive systems during the war's crucial years. The 57% kill ratio achieved by B-24 ball turrets against German fighter aircraft demonstrates the mathematical precision that Sperry Corporation engineers built into their K-4 computing sites, while the psychological impact on enemy pilots proves equally significant in degrading Axis fighter effectiveness. American technological superiority becomes apparent not just in the quantity of weapons produced but in the sophisticated integration of multiple technologies into systems that exceed the capabilities of enemy equivalents. The legacy of World War II ball turret operations establishes precedents for technological development that continue shaping military systems in the modern era. The principles of computer-controlled defensive fire pioneered by Sperry Corporation find expression in contemporary air defense networks and automated weapon systems, while the integration of gyroscopic stabilization and ballistic computation influences everything from guided missiles to spacecraft navigation. The mathematical precision that made American ball turret gunners so effective against Axis fighter aircraft represents an early example of the technological advantages that characterize modern warfare. As the war concludes in victory for Allied forces, the contribution of ball turret gunners receives recognition in official histories and veteran memoirs, their technological sophistication and individual courage helping determine the conflict's outcome. The young men who operated Sperry ball turret systems returned to civilian life carrying the knowledge that their mathematical precision and industrial superiority played decisive roles in defeating fascist aggression. Their legacy lives on in the continued development of computer-controlled weapons systems that trace their origins to the innovative engineering of World War II America.